Hello, I hope you're doing well. In this video, I want to share with you the journey that I went on to design and manufacture the brains of the mechanical part of Jugglebot. Now, this is not to be confused with the big brains of Jugglebot, which will be doing all the computation required to move the hand and the arm into the correct place, given where the balls are at any given time. That's for a later video. But this one is to cover this circuit board design here, which has the objective of taking in information of where the arm needs to be and moving the motors into the correct place. This is the first time I have ever designed a PCB, a printed circuit board, and it was a little bit tricky in some parts and pretty fun overall, I would say. So in this video, I want to go through everything that I had to do to design this board and to get it to do what I want it to do, so that hopefully, if you have a similar project, you can make it a little bit easier for yourself after having watched this. So before we get into any of the details, it's worth understanding why I actually need to have this at all. Because at the end of the day, all that I really need is a microcontroller, so like a Raspberry Pi or an Arduino or something like that, and just plug that straight up into my motor drivers, and then off I go. But unfortunately, life is never quite that simple, and it didn't quite work out that way. The reason for that is because inevitably there is almost always something that has to go between the motor drivers, in my case, and the microcontroller. And even if there isn't, plugging things into these little tiny pins here is a little bit tedious, and it's a lot easier to do that if you have a nice circuit board that lays everything out and gives you nice little plugs to plug everything into that you need to. Now, before I could actually get into any nitty-gritty details, I first had to decide what microcontroller I was actually using. And I was previously just using Arduinos because that's what I had on hand, but I pretty quickly ran into a problem, which is that using the stepper library that I'm using for the Arduinos, the maximum steps per second, so like how many times I can get the stepper motor to move every second, using that stepper library, which is called AccelStepper for anyone interested, is about 4,000 steps per second using a normal Arduino. There are some Arduinos that you can get that have a higher clock speed and can hence output more steps per second, but with everyone's favorite silicon shortage going on right now, those are in high demand and are not super cheap, at least in Australia. And for what I'm doing, 4,000 steps per second is just not going to cut it. But how many steps per second do I need? Well, I know that I want the legs to have a maximum speed of 0.7 meters per second, which is very fast, and it's yet to be seen whether or not I'll actually be able to get them to move this fast, but we'll see. But that's at least my goal. And knowing that linear velocity of the legs and the characteristics of my ball screws that I'm using to drive the legs, I know that I will need to spin that screw at 175 revolutions per second. And using the motor drivers that I'm using, which are DM556 drivers, the minimum number of steps per revolution that I can send is 400. So if I want the motor to spin at 175 revolutions per second, and I'm sending 400 steps per revolution, that means I need 70,000 steps per second, which is quite a bit more than the 4,000 steps per second that an Arduino can output. Now, this divide between what the Arduinos can output and what I need is made even greater by the fact that I have not one, but 6 of these motors. So in the worst case scenario, when everything is moving at maximum speed, I'll be needing around 420,000 steps per second. Again, it is yet to be seen whether or not I will actually be able to achieve this because of other constraints, but that's my absolute upper limit of what I'm going to be aiming for. So I absolutely needed something faster than the Arduinos. And after a bit of searching around, what I came up with is the Teensy 4.0, which has a clock speed of 600 megahertz, which is about 60 times faster than the Arduinos. So it probably still won't be able to output 420,000 steps per second, but it will be able to do a heck of a lot better than the Arduinos. And if I need to, I might be able to figure something out where I chain up 2 or even 3 of them to divide the load between each other. I don't really want to have to do this because that's going to mean syncing them all up together, but that's a problem for later. After reaching that conclusion of needing to use the Teensy 4.0 to give me the higher step rate so that I can move my motors faster, I ran into another problem, which is that the DM556 drivers take in 5 to 24 volts for their logic controls. And this is fine for the Arduinos because the Arduinos output 5 volts as their logic current or as their logic voltage, and that's all great. So I can just connect the Arduino straight up to the DM556 and it's good to go. But the Teensys output 3.3 volts, which is definitely not 5 volts. Now, after reading a little bit online, I saw that some people have gotten away with just outputting straight from the Teensy to the motor driver and they haven't had any issues. But from what I can tell, this seems like it's a recipe for potential disaster, and it's just giving yourself another place for problems to come up later in the future. So if there is like a microwave in the room, or if you've got really strong lights or something, you might have issues with your motors and you're going to be sitting there scratching your head thinking, where are these problems coming from? They weren't here before. And in reality, it's just the fact that your voltage isn't high enough to reliably trigger a signal. I didn't want to have to do that, and I wanted to make sure that I eliminated this source of error before it even started. So I had a bit of a look around, and the best solution that I could find for this is to use logic shifters. So these little tiny integrated circuits will take in 5 volts as well as, in this case, 4 input signals, and then steps that input signal up to 5 volts and then sends it off to, in my case, the motor driver. So this little chip saves me because it turns the 3.3 volts out from the Teensy into 5 volts, which will then reliably trigger the motor driver, and I won't have any issues with noise or anything else going on in the room that could stuff this up. So this will make my system a lot more robust, hopefully, and it should stop a lot of those issues from coming up. Now, by this point in my research for this project, I was still thinking that I would be able to get away with just doing this on like a breadboard or doing it on a Vero board and soldering everything together myself. And to be honest, that still probably would have been okay. But after building this on a breadboard just for one logic shifter, I realized that this is just going to be a mess and I don't want to have to deal with this. These cables come out really easily and it doesn't look nice and they're an absolute pain in the butt to put in and to line up correctly, and it's just not very nice. That is amplified even further by the fact that I need 3 of these logic shifters. Each one outputs 4 signals. Each driver needs 2 input signals, which means that each logic shifter with its 4 output signals can output to 2 motor drivers, and I need 6 motor drivers, so I need 3 logic shifters. Multiplying this by 3 did not sound very fun to me at all, so I never stepped beyond the point of just getting one logic shifter set up on the breadboard just to validate the concept, and then I knew that I had to move on to something a little bit more robust and neat. Now, I probably could have gotten away with doing this on a Vero board, which is, for anyone who doesn't know, just like a board with lots of pins in it, and there's like there's like copper traces through it, so that way you can plug everything in and then solder all of the traces together as you need to. And if you want to break any traces, you can just like cut them or break them, basically, like physically break them. And that probably would have worked, but I sort of wanted to have a PCB for this just because I wanted to try making one and I wanted to see what that process was like. I'd heard that it was relatively inexpensive nowadays and it just sounded like fun. So I looked online to see how to do this, and it turns out it's actually not too tricky. So now I'll show you all the steps that I had to go through to make this circuit board a reality. Now, the very first thing that I would suggest going into this is to have a very good idea of exactly what you want your circuit board to achieve before you even start drawing it up on any programs. Because I had to go back and change things 2 or 3 times, and as you will shortly see, it's quite tedious to do that in the software, at least the software that I'm using. And yeah, so the further that you move through this process, the less and less you want to be needing to go back and make changes, because it's very tedious to do that. So what do I need for this circuit board? Well, I need a spot to house my Teensy 4.0, and that has to allow me to connect all of my pins up so that I can route them out to everything else. I will also need the 3 logic shifters, which will step up the 3.3 output volts from the Teensy up to 5 volts to go out to the drivers. I also need some way of connecting all 6 motor drivers to the board so that those signals can actually connect through to the Teensy ultimately. And I also need 6 inputs for the limit switches on Jugglebot's legs. Now, if you haven't seen my earlier video on linear actuators, it doesn't really matter for right now, but suffice to say, I have a limit switch on every single leg driving the Stewart platform of Jugglebot, and I need some way to get those signals into the Teensy. Additionally to all of that, I need some way to power this whole setup. Now, thankfully, the logic shifters and the Teensy both take a 5-volt input, so I just need some way of connecting 5 volts to the board, and then I should be good to go. So now that we know exactly what needs to be on the board, we can go into this program to start to actually design everything. Now, the program that I'm using here is called KiCAD, or I've also heard it pronounced KiCAD. I don't know which one is more correct. I've just been calling it KiCAD. I think KiCAD sounds better. It's a free software, it's pretty easy to use, and there's plenty of tutorials online for it. And this is what my schematic looks like for this circuit board that I've made. You can see that it's quite messy, and I will get to exactly why that's the case in a sec. But the general overview here is that you input the parts that you want. Like for example, this block here is the Teensy 4.0, and you can see on each part all of the different pins that that part has. So yeah, here's the Teensy. It's got 54 pins in total. And then over here is one of the logic shifters, and that's got 14 pins. And these are all nicely labeled to show me exactly what they all are. Now, using the data sheet of the logic shifters and knowing what the pins are for the Teensy, you can go ahead and wire everything up. And this is relatively straightforward. If you just hover over an element, you can press W, and then you can draw your wire and connect it wherever you want to. And this is the way that I was doing things when I first opened up this program, and I was just connect, and having a grand old time. But then that very quickly gets quite messy. And I thought I was being very clever by coloring my 5 volts line red and my ground line black, which is very tedious to do, by the way. But it turns out that this whole way of doing things is a little bit silly, because what you can do instead is just label what all of the different lines are, and then KiCAD knows in the next stage of the program that those things have to connect to each other. Like for example, here is hub to L2, and over here is hub to L2. So when we go to the next stage of the program, which is to actually lay out the PCB itself, KiCAD knows that those two things have to be connected to each other. It's exactly the same schematically as these green lines are, but that's a lot easier to follow and to understand, assuming you're using a sensible writing notation, than these green lines are. Once you've got them all set up and laid out, you can then head over to the PCB editor, which looks like this. Now, unfortunately, the program is not capable of plotting everything out and hooking everything up exactly the way that is shown here by itself. And I think that's sort of sensible because the program doesn't know exactly how you want things to be laid out. So I think that's ultimately actually okay. What you actually see when you open this up is a whole bunch of parts just plonked down, and you'll see a whole lot of these gray lines connected up. And these tell you exactly what needs to be connected to what. For example, it's showing me here that pad 2 needs to connect to this line here for the circuit to be correct as I have outlined it in my schematic, which was the previous step. Now, there are plenty of tutorials online that can cover this much better than I will be able to here, but one thing that I will suggest, because I didn't really see this emphasized in the tutorial videos that I watched, is to be very, very deliberate with the way that you lay all of the geometry out before you start routing the traces. I was a bit excited when I first went into this program, and I just sort of plonked things down where I thought they just sort of made sense and then started routing all the traces. But as you just saw, whenever you move a part, it doesn't move the traces with it. So you're going to have to reroute everything to get it all to make sense again. And that process is very, very tedious if you have to do it for, honestly, even just like one single part. It's not something you want to have to do over and over again, as I did. It's a very, very tedious process. So once you've got all of your geometry laid out and everything is exactly where you want it to be, then you can start routing all the traces and putting in the mounting holes and all of that sort of stuff. And that's not actually too tricky. It's kind of fun actually to connect everything up. One thing that I would just quickly add, which I didn't really talk about before, is this serial connection here. The reason for this serial connection is that this board is eventually going to be connected to Jugglebot's actual brain, which will be telling this exactly where to move all of the legs in any given time. I'm not exactly sure how that connection is going to work. It may end up just being through the micro USB port up here, but I was not exactly certain of that, and it may end up being easier to just connect it straight up with a serial connection. So I've just included this in here just in case I need it in the future. Everything else on this board is exactly as I described it before, where we've got the 3 logic shifters, the 6 pairs of pins that will go out to the limit switches of the legs, as well as the 6 connections that will go to the drivers for all of the legs. And so now that the board is fully laid out exactly how I want it to be, with all of the traces laid out correctly, the only final step remaining is to save the board as a Gerbil file, which you can do up in File and down in Plot. This doesn't come up for some reason properly in the recording, but it's in Plot. And you just save it as a Gerbil file and then upload that to your PCB manufacturer of choice and fill out all the settings on there, and then you're good to go. I used a company called Next PCB just because they were the cheapest for what I needed. And it was a pretty straightforward process to upload the Gerbil file and go through all the different settings and get the PCBs made. Now, something that's probably quite worth knowing before you go into this process is that it's not really practical to order just a single PCB. They just don't operate on that sort of scale. In fact, with most PCB manufacturers that I saw, the minimum order quantity is actually 5. Now, that may dissuade you from getting a custom PCB made if you only need 1, as I do here, but I still wanted one because it's pretty cool and it's nice to be able to say, here's a PCB that I designed and it actually works. And also it's not that expensive anyway. So despite only needing 1 board in reality, I ordered the minimum quantity of 5 and I actually ended up getting 10. So now I have a whole stack of PCBs that I can use in case I ever break this one or when I make subsequent Jugglebot arms. So these will come in handy, but just be aware that you can only buy a minimum quantity of 5. Now, something else that I think is worth me pointing out, and something that I did not read before going into this PCB design process, is to have a careful think about what things physically look like and how big things physically are before you finalize your PCB design. Now, when I was designing this PCB, I was planning on using little header pins for the switches, and those are quite small, but between when I designed the PCB and had it shipped off to get it manufactured and when it actually arrived, I decided to switch that because those little header pins aren't really that secure. They just sort of like sit in there and nothing really actually holds them in. I decided to swap that for instead using JST connectors. And these connectors are great because you can actually like plug them in and they sit in solidly, but they have a problem, which is that the female part, the connector part, is quite a bit larger than the pin headers. And this posed a problem because I wasn't planning on using these and I didn't really allocate enough space between the switches for JST connectors to fit. This is a stupid mistake for me to make because I've got heaps of space here. I've got more than enough space to fit all of my JST connectors in here, but because it looked nicer in the program, I wanted to have them all nice and sort of like compact. So now the JST connectors don't really fit properly. Thankfully, there is just enough room that if I cut apart one of the JST connector ports, then everything fits nicely, but it's definitely not the most elegant solution out there. I should have realized that I have plenty of space there, and even if I am using pin headers, it's okay to have a little bit of space between everything. And I should have just padded out all of these switch pins to put them as far apart from each other as I could without increasing the size of the board. That is a pretty important lesson that I have learned in PCB design, and I will absolutely not be forgetting that one anytime soon, because that really could have cost me if they were any closer and I just would not have been able to use those connectors or this board if that were the case. And that would be a bit of a bummer. Something else that I am taking away from this as a pretty valuable learning experience is to make sure that the mounting holes have a sensible distance between them. Sensible being usually to the nearest millimeter or 5 millimeters or inches if you swing that way. but just make it something sensible. In my case, when I was in KiCAD and I was lining everything up, I just made sure that they were all lined up with each other. And I wasn't really thinking about how far apart they were from each other. And I should have done that because now these ones are something like 22.53 millimeters apart. And these ones are like 114.62 millimeters or something stupid like that. And so now when I'm going into CAD to design the thing that actually holds this, I have to deal with that sort of nonsense. And it would have been nice if it was just a nice even 115 and 25. So lesson learned for next time. The final meaningful change that I would make to this design if I were to do it again would be to have some way of connecting to the remaining pins on my Teensy. So right now I've only connected up the pins that I need to be able to interface with my switches and my motor drivers, but it would be nice if I needed to be able to connect other things up to this as well. Now I could, if I need to, solder onto the top of my Teensy or even on the back side. There's pins sticking through, so there's plenty of room there for me to solder onto, but that's sort of defeats the whole purpose of having this nice, compact, tidy PCB. What I would do differently is have just a bunch of holes where I can attach pin headers or other JST connectors or something, so that way I can actually access the rest of the pins on the Teensy. Alrighty, that just about takes us to the end of what I had to go through to design and manufacture a circuit board for Jugglebot's mechanical side of things. This was certainly a very valuable learning experience, and I have come away with this much more adept at designing PCBs, I would like to think. And it's been a pretty fun experience. I would strongly recommend that if you ever have any projects where you're getting sick and tired of this nonsense and want to have something that's a bit more nice and neat, that you at least consider doing this yourself. It's a very fun experience. It's quite tedious, but it's very rewarding as well. It's really, really nice to be able to look at this and think, yeah, I made that. I have found myself constantly over the last week or so just picking this up, just having a look at it, and then putting it back down and continuing on with my day. Even though it's the most basic board ever, like it doesn't really actually do that much. That's complicated. And yeah, so I hope you learned something in this video, and I will see you in the next one. Till then.